In the second part of our worksheet, we're going to look at the Pythagorean Theorem. Recall the Pythagorean Theorem is a squared plus b squared equals c squared. And this only works for a right triangle. The legs of our right triangle are the legs A and the legs B. The longest side of our triangle is always labeled C, and that's known as the hypotenuse of the triangle. Now remember, this formula only works for right triangles, triangles with a square corner. A squared plus b squared is equal to c squared. Again, A is a leg, the B is a leg, and the longest side C is known as the hypotenuse. Question 1. A right triangle has a hypotenuse that measures 12 inches and one of its legs is 10 inches long. Find the length of the other leg to the nearest tenth of an inch. So let's draw ourselves a picture. We know the hypotenuse is 12 inches and one of the legs is 10 inches. So we don't know what this distance here is. Let's give it a name. We'll label it as B. So I know a squared plus b squared is equal to c squared. So I can rewrite this as 10 squared plus b squared equals 12 squared. 10 squared is equivalent to 100. And b squared is just b squared. 12 squared is 144. To solve for b, we can subtract 100 to both sides. And I have b squared equals 44. Now to solve this, we can take the square root of both sides. Don't forget to include the plus or minus symbol when you take the square root of both sides. So we have b is equal to plus or minus the square root of 44. But it doesn't make sense to have the minus symbol because the distance cannot be negative. So we're just going to throw out the negative symbol. So b is equal to the square root of 44. I can simplify this by breaking down 44 with a factor tree. That's 2 times 22, and 22 is 2 times 11. So I can rewrite this as the square root of 2 times 2 times 11. And since I'm looking for groups of 2 for square roots, this is equivalent to 2 root 11. And we could use a calculator for this problem. B is approximately 3.6 inches long. So the length of the leg is about 3.6 inches. Question 2. Claire routinely bicycles across a rectangular parking lot on her way to work. If the lot is 200 feet long and 150 feet wide, how far does Claire travel when she rides across the lot diagonally? So let's draw a picture so we can understand this problem. We have a rectangular parking lot and she's going to ride her bicycle diagonally. It is 200 feet long and 150 feet wide. Notice that we have two right triangles. We have a right triangle here and a right triangle here. Since this is a rectangle, this must be 150 feet and here must be 200 feet. So now we could use the formula a squared plus b squared equals c squared to solve for our hypotenuse. I can write 150 squared plus 200 squared must be equal to c squared. 150 squared is 22,500 and 200 squared is 40,000, and that's equal to c squared. We can add 22,500 with 40,000. That gives us 62,500 is equal to c squared, and we could take the square root of both sides now. Don't forget the plus or minus, but in this case, we don't care about the negative because we can't have a negative distance. So we can use our calculator now. The square root of 62,500 is equivalent to 250. Now we're talking about a distance here, so we know that Claire must ride 250 feet across this rectangular parking lot. In this question, we want to simplify if possible. Assume that all variables represent non-negative real numbers. Write your answers as radical expressions when necessary. So at the end, we want to make sure our solution is in radical form. But before we do that, let's recall some exponent rules that we should already know. The first rule, this is the product rule, x to the m times x to the n. We're going to add the exponent. This is x to the m plus n. The second rule is the quotient rule. X to the m divided by x to the n is equal to x to the m minus n. This is the quotient rule. The third rule is a exponent to a power rule. X to the m raised to the n. We're going to actually multiply the exponents. This is x to the m times n. For the fourth rule, this is x times y raised to the n. A product raised to a power is equivalent to x to the n, y to the n. And for our fifth rule, we have a quotient raised to a power. That's x to the n, y to the n. For the sixth rule, we have x to the negative n, which we have already gone over. This is equivalent to 1 over x to the positive n. Now we know some of the exponent rules. Now let's get started with question 5. We have b to the 9 over 10 divided by b raised to the 4 over 5. This is equivalent to b raised to the 9 over 10 minus 4/5. Now I cannot subtract these exponents because they have different denominators, so let's multiply the top and bottom of the second fraction by 2. We have to multiply the top and bottom of the second fraction by 2. And this simplifies to b raised to the 9/10 minus 8/10. And I can subtract 9/10 and 8/10. This gives me b raised to the 1 over 10. But in the directions, we want to make sure it's a radical. So let's rewrite this as the 10th root of b. And this completes question 5. For question 6, I'm going to use the product rule. This is equal to x to the 5/18 plus 7/18. And since they have the same denominator, that's really nice. This is x raised to the 5 plus 7, that's 12 over 18. But I can reduce the 12 and the 18. They both have a common factor of 6. So let's divide the top and bottom by 6. We get x to the 2/3 power. But we have to write our solution as a radical, so let's rewrite this as the cube root of x squared. Now this is a good solution. It is also acceptable to write this as the cube root of x quantity squared. So they're both good solutions. You can decide to rewrite it in any way that you want for question 6. For question 7, I'm going to use the product to a power rule. I'm going to take that 1/2 and multiply it to each and every single one of these exponents. So this is equivalent to 48 to the 1/2 power. There's an invisible exponent of 1 for the 48, and that's what I'm multiplying with the 1/2. So that's 48 to the 1/2, and this is x to the 20 times 1/2, which is 10. We have y to the 34 times 1/2, which is 17. But we're not done yet. We have to simplify 48 to the 1/2. That's equivalent to the square root of 48. X to the 10th and y to the 17th just follows along. And let's break down 48. I know 48 is 2 times 24. 24 is 2 times 12. 12 is 2 times 6. And 6 is 2 times 3. So this can simplify as the square root of primes. 2 times 2 times 2 times 2 times 3. Don't forget the x to the 10th, y to the 17th. Now what are we looking for? We're looking for groups of 2. So I have 2 times 2 to the front, which I can replace with 4 in the next step. We have x to the 10th, y to the 17th. So this is our final solution. We can multiply the 2 times 2. That's 4 with the square root of 3 left on the inside. X to the 10th, y to the 17th on the outside. This is our solution for 7. For question 8, you can try it with the same technique we did in question 7. We'll take that 2/3 and we'll multiply it to each and every one of these exponents. So this is 512 raised to the 2/3. Again, there's an invisible exponent of 1. This is x to the 54 times 2/3. And this is y to the 1/17 times 2/3. So we're using the same strategy we did in the previous question. Now 512 raised to 2/3, I could write that as a radical. That's the cube root of 512 raised to the second. And 54 times 2/3, you can simplify this. 54 times 2/3, you can just use a calculator for that. That's going to be x to the 36. And we could also use a calculator for 117 times 2/3. That gives us 78. And now we could simplify the cube root of 512. That's going to be 8. You can use a calculator or you could use a factor tree for that part. So this is now 8 raised to the second times x to the 36, y to the 78. And 8 squared is 64. So this is our solution, 64, x to the 36th, and y to the 78th. For question 9, we're going to identify the property illustrated by each expression. For the first one, 3.2 plus x is equal to x plus 3.2. So it doesn't matter which order we add, it's going to give us the same solution. This is known as the commutative property. The commutative property. Part B, we have 1 times b equals b, and b times 1 equals b. This is also the commutative property because it doesn't matter the order of the numbers. We can switch them around and we'll get the same answer by multiplication. This is also the identity property when multiplying. When we multiply by 1, we're going to get the same thing. For part C, it looks like we have to multiply the 1.5 times x and the 1.5 times 10 to get this result. This is known as the distributive property. The distributive property. In question 10, we want to write an expression to illustrate the indicated property of real numbers. The associative property. This is the one where we can move the parentheses and still get the same answer. So let's try 1 plus 2 plus 3, and that should be equal to 1 plus 2 plus 3. Notice in the first part we have the parentheses around the 1 and the 2. That gives me 3 plus 3, and that's equal to, we have 1 plus 5 here on the right because we're supposed to do 2 plus 3 first. And what do you know? You get 6 equals 6. So this is the associative property for addition. We can do the first 2 terms or the second 2 terms first, and we still get the same solution. In part B, we want to look for the 0 property for multiplying. And that means if I multiply 2 times 0, I always get a 0. And that's equal to 0 times 2. So that's the 0 property for multiplying. If we multiply by a 0, we always get the 0 back. For part C, we'll have to show the denseness property of real numbers. In order to show that, we have to consider numbers a and b and find the number c between them. So let's give an example. Let's say 5.5 and 5.6. According to the denseness property, you'll always be able to find a real number between 2 real numbers. So let's find a number between these 2 numbers. Let's say 5.55. This property works between every two real numbers. You'll always find another real number between two real numbers, and that's why we have infinite real numbers.